Okay, so we're going to talk about multicast and packet replication in distributed systems. So today on the public internet, we can draw a simplified validator group here of just 4 nodes, but this scales out to thousands of nodes as well. When you look at this and you say, okay, so this validator right here, they're producing a block. What has to happen once a validator produces a block? Well, a bunch of stuff has to happen, but before consensus can be reached, before votes can be had on that block, the data actually has to propagate from this node out to all of the other nodes in the system, or at least a quorum enough to reach consensus. So what happens today? So on the public internet, this node will send 1 copy of the data to that validator. It'll send 1 copy of the data to this validator, and it will send a 3rd copy of the data to this validator over here. So the entire burden of state propagation is on the block producer. And there's a few sort of things that come with that. One of the main downsides that come with that is this validator needs enough bandwidth to send packets out to all of the nodes that it needs to get to anywhere in the world within its allotted time to produce a block so the network can reach consensus and keep moving forwards. Now, in this model, you say, okay, this is only 3 copies of the data. But suddenly you look at a network like Solana, you look at a network like Ethereum, where there are thousands and thousands of validators located all around the world, and you can suddenly see how even if you're only trying to move a few megabytes at a time of data, this rapidly becomes a bandwidth multiplication problem. Suddenly, this validator has on its hook the ability or the responsibility to send data out to thousands of different nodes all at the same time. Now, the way this is solved, or at least attempted to be solved in networks like Solana and Monad, are through technologies like Turbine and Raptorcast. And in both of these models, the network basically builds trees. So you'll have other validators out here, and they will send copies to each one, and they will send copies to each one, and they will keep sending copies around. And so what this does is this reduces the load on the individual validator that produces the blocks, and now maybe this validator is sending to 200 of its neighboring nodes as opposed to 2,000 of its neighboring nodes. But all we've done is really hoist that work onto other participants in the network. The aggregate amount of bandwidth required to reach consensus actually is increased, not decreased in this model. And so we still have massive amounts of data replication, and it increases the load on each of these validators. To make this process worse, these networks are not designed today in ways that make themselves geographically aware. So this validator right here might be in Singapore. This validator here may also be in Singapore. And this one may be located in Amsterdam. And so we have data moving from Singapore to Amsterdam back to Singapore, which is a really inefficient way to move anything around the world. It's sort of like the worst routing problem you can imagine for your FedEx package. So what do we do in a multicast world? How is this solved in private networking, and how is this addressed in companies like high-frequency trading firms? And how is doublezero applying this technology to blockchain validators today? So we set this model aside for a second, and we look instead at a model where we'll start with another simplified version here, where we have 4 nodes on the system. And we have this validator that now has produced a block, and it needs to propagate that data out. So this is where things get interesting and fun. Multicast is a technology that is effectively hardware acceleration for packets and packet delivery. So what this does is when a packet enters the switch, that packet is tagged with something called a multicast group. And so you can say if all of these members are part of multicast group 1, when a packet is sent from this validator, it now, which it does here too, but it goes into a switch. And that switch, a doublezero device in this particular instance, says, okay, who else on the network needs to receive the packet? Are you part of multicast group 1 that has decided, hey, we want to receive all these types of packet data? And so the switch now is responsible for sending on data to multiple locations. So this does a few things. The first is it offloads the responsibility from the validator to the hardware layer to actually being able to send data out. This is a massive time savings and compute savings and bandwidth savings for this validator, because while this link connecting the validator to the switch may only be 2 or 10 gigabits per second, the switch, the bandwidth available to this switch on the backhaul can be significantly larger than that. And so it has the ability to replicate data out to multiple places. But let's add a few more nodes and see where things get even more interesting. So now we have 3 nodes here, we have 3 nodes down here, and let's just for fun put another node over here. In this model, as you can see, there's 3 copies of the data sent out from this node to 3 different switches. With multicast, what will happen is we've completely offloaded this from the switch's responsibility. So instead, you have another 00 device, which again is just basically a fancy term for a network switch. And this switch here will send data over to the switch, which then in turn sends copies out to the 3 nodes connected to it. Now this may not seem like a radical departure, but let's just say, for example, all of these here are in Singapore, and we're starting in Amsterdam here. And then we have another one over here, let's say in Amsterdam as well. What we've done is we've reduced the amount of long-haul bandwidth and the amount of, from a replication factor of 3 to a replication factor of 1. Because now the network layer is responsible for saying this packet moving from here to here will get replicated at the end. So you can think of this as sort of removing the amount of bandwidth that needs to go from the core and pushing it out to the periphery of the network. Additionally, we solved this problem here of the Singapore to Amsterdam to Singapore back loop because, for example, if this one is also located in Amsterdam, the switch will send it on directly. One of the advantages of multicast is it is geography aware and route aware. So in our traditional model here, which is what public blockchains use today, the node in Singapore is not thinking, oh, I need to get data to another node in Singapore. All it knows is I'm supposed to send data to these various participants. In a multicast network, the switches are responsible for automatically configuring and figuring out what is the shortest path possible to get data from where it started to all the different places it has to end up. And that will always occur over the shortest pathway that requires the least amount of bandwidth and the least amount of data replication. So this is all to illustrate the problems today facing modern blockchains are actually that of communication, not compute. The speed at which you can propagate state from one node producing a block out to 2,000 nodes who need to reach consensus on it is the limiting factor in how fast blockchains can move today. It's not compute, it's not something else, it is that fundamental underlying communication rate. And so multicast as a technology is a step function change in what's possible in terms of data propagation. And this technology, combined with private dedicated fiber, can accelerate the pace of blockchain adoption and allow networks to reach millions and millions of transactions per second, which they're currently not able to do without relying on extreme centralization. Multicast is one of those technologies that can really enable a permissionless, open, globally distributed future without having to sacrifice performance.